So yeah, I'm going to talk about quantum Markov semigroups and their applications in fundamental algebras, and specifically to the Akemann Ostrand property. So I will start with introducing what I mean by a quantum Markov semigroup, because that's not a thing that people agree on. So in my talk, so I will always stick to finite fundamental algebras. So fundamental algebras equipped with a normal faithful trace and a semigroup of unital completely positive maps will be called Markov if it satisfies the following conditions. So it preserves the trace on the level of the L2 space, the GNS space. It is self-adjoint, so it has a symmetry with respect to the trace, and it is strongly continuous. So, or for example, continuous on the level of L2. So as the time t goes to 0, the operators converge to identity. So these objects are very useful in proving approximation properties of fundamental algebras. So here is a sample of known results. So if you can prove that on your fundamental algebra there exists a quantum Markov semigroup with a specific decay property, then for example you can characterize amenability in this way. That's what Cipriani and Sauvageot did, and also you can characterize Hager property. So it was done also in the tracial case by Leuven and Martijn, and by Caspers and Skalski also in the non-tracial case. And these characterizations, they really resemble the characterizations of the corresponding approximation properties for groups. So, for example, for amenability, you can characterize via existence of positive definite functions which are in L1 but converge to 1 pointwise. So, and the Cipriani-Sauvageot result is basically saying that if you have a semigroup such that the maps PT are trace class, which is basically a non-commutative analog of being L1, then you have amenability. So, and the corresponding characterization of Hager property. So for groups, this is existence of positive definite functions which vanish at infinity and go to 1. And for fundamental algebras, this is just compactness of the operators in the semigroup PT. And there's another approximation property which is very useful, and it will also appear later in this talk. This is the completely bounded approximation property, and this is and existence of nice quantum Markov semigroups is also useful for obtaining that. Okay, so my talk will be about a common theme in recent years in fundamental algebras, where people study uniqueness of the compositions of fundamental algebras into, say, sort of simpler blocks. So I will talk about 2 ways of building fundamental algebras. One is the tensor product, and the other is the so-called group measure space construction. So when you have a group acting on a probability space in a probability preserving way, then you can build the cross product. So there are 2 ways. I mean, there are 2 problems at hand. So one you can study in what ways your fundamental algebra decomposes, maybe using these constructions. But sometimes you might want to prove that it's actually indecomposable, that you cannot make it any simpler using these constructions. And this is what strong solidity gives us. So this was the property introduced by Ozawa and Poppa in their seminal paper. So it says that a fundamental algebra is strongly solid if for any diffuse amenable subalgebra. So diffuse means just no discrete part. The normalizer, so the unitaries in the algebra that conjugate A against into itself, that this remains amenable. So for example, so this was tailor-made to exclude existence of decompositions via group measure space construction, because then the normalizer contains the group elements and the subalgebra, so it would be everything. So as soon as your group is non-amenable, yeah, then it could not be strongly solid. Okay, so strong solidity is somehow, it's a technical property which allows to prove that the fundamental algebra doesn't decompose as a tensor product in a non-trivial way, and also it doesn't decompose as a cross product, as a group measure space construction. So how would we go about proving such a property? We could use the so-called Akemann Ostrand property. So this was first observed, of course, by Akemann Ostrand for the free groups, but the general property was defined by Ozawa. So M would be a 2-1 factor. And if there exists a weakly dense C-star subalgebra of M that is locally reflexive, it's just a technical condition, but for example, exact. So for example, for all exact groups, this would be easy. So that's just a technical condition. I don't want to talk about it that much. And such that the left-right action of A tensor A op on the L2 space of your phonome algebra, after you mod out the compacts, that this is continuous with respect to the minimal tensor product, then we say that the M has Akemann Ostrand property. So without the compacts, this would be just characterization of amenability. So, and we want to talk about non-amenable phoneme algebras. So somehow it feels that it's close to amenability, but still strong enough to yield interesting results about non-amenable things. And then, so I mentioned also that there is a definition due to Isono. So this is a slight extension of this definition. So we have that this map into the quotient is mean continuous, and we have a map into a quotient. Then of course it's natural to ask about existence of lifts, and if there exists a UCP lift of this map, then we say that this has the property AO plus. And then the theorem obtained by Isono, greatly inspired by the paper of Popa and Vass, is that if you have a 2-1 factor with the completely bounded approximation property and this AO plus property, then it is strongly solid. Okay, so now I will want to talk about a strategy of proving Akemann Ostrand property, the property AO plus, but I need some preliminaries. So I have to talk about bimodules. So for phoneme algebras, a bimodule is just a Hilbert space equipped with both a left and the right action of a phoneme algebra. So what are the examples? There is just the trivial bimodule, so just the L2 space of the phoneme algebra with the left and right action. And then there's also the very important coarse bimodule, where the left action just acts on the left leg and the right action is just on the right leg. And a theory of bimodules over phoneme algebras is what unitary representations are to the theory of groups. And then the trivial bimodule actually would correspond to the trivial representation, and the coarse bimodule to the left regular representation. And just like for representations, there is a notion of weak containment, and we will need that later on. So I will not specifically define it, but I will say that if a bimodule H is weakly contained in the coarse bimodule, then the left-right action is mean continuous, because obviously the left-right action on the coarse bimodule is continuous with respect to the minimum tensor norm, because it's completely split between the two legs. Okay, so in order to obtain the property AO plus, we would look for some bimodules which are weakly contained in the coarse bimodule. So we're going to need the following ingredients. So we're going to need a weakly dense C-star subalgebra, a bimodule which is weakly contained in the coarse bimodule, and we're going to also need an isometry that is almost bimodular. So isometry from the L2 space into H that is almost bimodular. We cannot hope which means that this if you first act and then apply the isometry, or if you first apply the isometry and then act from the left and the right, that this perturbation is compact for any elements of the C-star algebra. So we cannot hope for a really bimodular isometry, because if H is weakly contained in a coarse bimodule, this would show that L2 is contained in H. This would mean that L2 is weakly contained in the coarse bimodule, and this is a characterization of amenability. So we would have an amenable phoneme algebra, and these are the ones that we actually don't want to work with. So if you have these ingredients, how would you prove property AO plus? Well, this is summarized in the following diagram. So the northeast arrow. So this is exactly the left-right action of A on the bimodule H. So since the bimodule H is weakly contained in the coarse bimodule, this is continuous with respect to the minimal tensor product. Then to go back to B of L2 of M, we conjugate by the isometry S. And in this way, we get obviously a UCP map, phi twiddle, because this is essentially its time spring dilation. And because S is almost bimodular, if we quotient out the compacts, this will agree with the left-right action of A on L2 of M, also with compacts modded out. Okay, and now I want to come back to quantum Markov semigroups because they actually are a source of bimodules and as well as such isometries. And there are some verifiable conditions, for example, for checking that such a bimodule is weakly contained in the coarse bimodule. So the construction is due to Cipriani and Sauvageot, and it should be somehow known from the classical theory. So if you have a quantum Markov semigroup, so on the L2 level, this is just a semigroup of self-adjoint contractions. And it has a generator, which is a self-adjoint operator. And we denote it by delta to suggest, for example, that the most classical case is the Laplacian, which is the generator of the classical Brownian motion. And for example, the Laplacian is the divergence of the gradient. So basically, we think that each such generator should be somehow a second-order differential operator. And in nice cases, it should be a square of a first-order differential operator, just like the gradient. And this is actually the case. So there always exists a derivation from the subalgebra A, which has to be defined, but it's some algebra, some subalgebra of M, which is contained in the domain of the generator. And there always exists such an algebra. I don't want to go into the details, but there's always exists a derivation into a bimodule such that delta is equal to del star del. And so we need conditions to ensure that H is actually, the bimodule is weakly contained in the coarse bimodule. And since we have this derivation, we can view A as a subspace of the L2 space of our phoneme algebra. So this would be a densely defined closable operator from L2 of M to H. We can take its polar decomposition and look at the polar part. So in the case, if this is injective, the polar part would be an isometry. If this is not injective, you have to tweak it a little bit, but that's not a big deal. And this polar part is actually reminiscent of the classical Riesz transform. And we need conditions for ensuring that this is almost bimodular. So I will next discuss these conditions, and then this will allow me to state the main result. Okay, so what are the conditions? So conditions about bimodules. So as I said, bimodules are just like unitary representations. I mean, not exactly like, but very similar. And they also have coefficients, just like unitary representations. But in this case, the coefficients are actually UCP maps on M. And then in the classical case, if you want to check that your representation is weakly contained in the left regular representation, for example, you can check that many of the coefficients are L2, then you get weak containment. Our analog of L2 is Hilbert-Schmidt. So if these coefficients are Hilbert-Schmidt, then we get weak containment. And this actually translates to very explicit estimates for the generator. And if this is the case, then we say that the quantum Markov semigroup satisfies the gradient Hilbert-Schmidt estimates. Then the second part about the almost bimodular isometry. So we can handle generators that somehow resemble proper length functions on groups. So first, we need properness. So we want our generator to have a compact resolvent. And we want a certain algebraic structure of the eigenspaces. So somehow we think of eigenvalues as lengths, and then if you have things of length n and m and you multiply them, then the results should have length at most n plus m. And what is more, the eigenvalues should not grow too fast. So in this length picture, the eigenvalues just grow linearly, so it would just be the length. In general, we want sub-exponential growth. And then in such a case, we call the quantum Markov semigroup filtered with sub-exponential growth. And then the main result is that if these conditions are satisfied, then we get the Akemann Ostrand property. So if M is a finite fundamental algebra and it admits a filtered quantum Markov semigroup with sub-exponential growth, and this semigroup moreover satisfies the gradient Hilbert-Schmidt estimates, which ensure the weak containment in the coarse bimodule, then it satisfies the AO+. And then if we combine it with Isono's result, then if the fundamental algebra has moreover the completely bounded approximation property, then it is strongly solid. So one example that I want to talk about, to which we can apply it. So first of all, we can recover many known results about free groups, about other types of groups, about quantum groups. But the main example that I want to talk about today is the example of q-Gaussian algebras. So so the q is the parameter between -1 and 1, and for q equal to 0, we get the free group factors. And we were able to compute exactly when a special type of semigroup satisfies the Hilbert-Schmidt estimates in this case. So hence we obtained the Akemann Ostrand property in this situation. So the exact condition is written on the slide. So it's the q squared times the dimension of the Hilbert space has to be at most 1. And what is more, we can also exactly compute when the operators that we want to show that were Hilbert-Schmidt belong to some Schatten SP classes. So this is a bit more general. And then the natural question is whether these Schatten SP estimates are actually useful, or whether only Hilbert-Schmidt things are useful. And it turns out that in the case of group fundamental algebras, actually, if you have Schatten SP estimates for some finite p, that this is sufficient, because if you have our bimodule which satisfies the SP estimates for coefficients, then taking a sufficiently high tensor power, we will obtain weak containment in the coarse bimodule. And using the group structure, you can also still get this almost bimodular isometry using, say, n-fold convolution. So this recovers some results of Thomas Sinclair about lattices in SON1 and SUN1. And the question that I want to leave here is whether this also works for general fundamental algebra. So whether SP estimates plus these filtered conditions and the sub-exponential growth are sufficient for obtaining property AO+. Okay, thank you very much for listening.